we will continue with Notebook 2, Tutorial 2, SuperSpike, which is the first application of an experiment on still one single neuron on hardware. Now, to give you a bit of context first, SuperSpike is a learning rule that will try to replicate a target spike train on one neuron, or on more neurons, but we will use it on only one neuron in this notebook. The target is we can calculate a Van Rossum distance between two spike trains. So naturally, it's a bit more involved to compare two spike trains, and the Van Rossum distance is a metric that allows us to do that. It basically measures the coincidence of spikes from your current spike train and compares that to a target. And minimizing this distance then means that we will learn a target spike train. There has been multiple publications that use surrogate gradient methods in order to learn spiking networks. We have a list of them here, and we will most intensively work with number one here, Friedemann-Zenke, which formulates surrogate gradients in a way that we can directly compute them and do not need to go through backpropagation in time or something like that. There's also work on our hardware in this list. So reference number 6 has used backpropagation through time. So not the exact SuperSpike algorithm, but still surrogate gradients in order to train the MNIST dataset of handwritten digits and the spike in Heidelberg digits dataset, which are spoken digits as a dataset. And yeah, just refer to these publications if you're interested. And we will, in this notebook, use the SuperSpike rule. There are much more details on the SuperSpike rule later, but as a brief overview, we will set up a network in Pine that uses a column of synapses with 25 inputs, but all stimulating only one neuron. And we will randomly select weights for those neurons and generate a target spike train with that, and only save the spike times of the spike train. We'll then reinitialize the network's weights, so just scramble it and have it learn to reproduce this target spike train with the same input spikes. So it has to learn to reproduce some weights. It will not reproduce the exact same membrane trace because it only learns to reproduce the spike train, not the whole membrane potential. But we will look at how this in the loop training scheme can be implemented directly using Pine in this notebook. Okay, first we will again import things. You will need to select the right kernel again in this notebook and then import everything that we need, mainly Pine, of course, and something that we need for plotting and NumPy and all that. We have
Sorry,
here,
Johannes, there's a request of zooming in a bit.
Another request of zooming in.
Yes.
Is this better?
And I think in view, you can set it to a presentation mode. Yes. Then the code
presentation mode.
Yeah, then the code
Did
is
that
just
change
a little
anything?
bit larger. Yes.
Okay. But I will still need browser zoom, even in presentation mode. Okay, if it works like this, we're fine. Okay, here we have another helper function that creates a figure. We will later plot membrane potential and an error trace, and we will need to update that, so not very interesting code here. And we will now start defining our network. Now I should say again, If you have any questions, just feel free to interrupt me, write in the chat, or just speak up here. Even if the question is just, please explain this line of code. So I think our group is small enough that we can do that. Okay, first we will define a number of inputs and an experiment duration for our experiment. This is right now only to generate the target spike train, but we will then reuse those parameters also for learning. This time step here is not required for the hardware. So the hardware, as you learned, is an analog system. It just runs. It's a physical model. It has no time step. But for our learning and also for the inputs that we will send, it's just much easier to work with NumPy arrays that are fixed time bins in size. So we define a time step here and make an array of times and time bins for that. Is the hardware async? So I think you're referring to async with respect to some external digital clock. So in principle, yes, but you can, in the beginning of your experiment, choose to reset the neurons or something like that, for example. So you could trigger an artificial reset on all membranes to have them start in a defined state. But afterwards, if you would not do that, they would just start at any time, as you just saw with the leak over threshold example that Christian showed, where the neurons just started at any time. And the neurons themselves, they are analog, so they don't have any clock in that sense or any time, any synchronization in that sense. They would only listen to external input and resets or something like that. Okay, let's continue with the notebook. We will also use a calibration. Technically, since we're only going to use one neuron in this notebook, it would not be that important to load a calibration for that. But since we're using external inputs, there are a lot of technical parameters that you would need to tune. And it's just easiest to load the calibration because we have it. So the calibration, we load it here and we inject it again in the Pine setup call. And we are now going to define a population of one neuron with the default calibrated HX neuron, which is a live neuron that will accept inputs and spike eventually. And we are going to create spike sources, 25 of them as we defined above. And we are also creating connections from all those inputs to the output neuron. And since a connection in Pine, a projection, is only excitatory or inhibitory, we are going to use two of them in order to allow signed weights. So our network should be able to just switch between positive and negative rates for the same logical synapse. But we are going to use two synapses in Pine, one excitatory and one inhibitory. And this also very much represents what we do on hardware. So also on hardware, our synapses can only be excitatory or inhibitory. And we will use two rows of synapses or two synapses combined with one of the rates set to 0 to achieve those signed rates. So there's another helper function, set weights, which now distributes the weights across those two synapses. So we clip weights first to the hardware range, which is -63 to 63, as we have 6-bit weights. And now writes positive rates to an excitatory part and negative rates to an inhibitory part. And that allows us now to have 6-bit plus sign of rate resolution, so to say. Now we will construct a set of input stimuli. We first fix a seed in order to make this experiment reproducible. and we define an input frequency. So we say we want to have Poisson spike trains with on average a frequency of 10 kilohertz. This would of course be an absurdly high number, but we have an acceleration factor of around 1,000 for our hardware. So this in biological terms would be something like 10 hertz. And on hardware with our speed up, we need to write 10 kilohertz of wall clock time. And now we are creating arrays in the time bins that we just had. So just draw random numbers, and if they are, if the random number is suitably, there's a spike, and if not, there is not. So that basically just creates a dense array, a Boolean array of spike times. And now we turn that into a list of output spikes. So only for non-zero elements in this Boolean spike train, we convert the times to milliseconds and append them to a list of input spikes that we now give to Pine and say, let this be the inputs for our population. Okay, so with a network defined and input stimuli defined, we can run the network and generate a target spike train. And we will use a random distribution of the synapse weights. So this column of 25 synapses will be set to a random weight of 27 in mean and 1 in standard deviation, at least by default. So let me just run this cell, and you have a slider then again that allows you to easily adjust mean and standard deviation of those weights. And here you can see the membrane trace. So you can see we have quite a bit of noise. These are all the inputs that did not yet lead to a spike. Eventually they stack high enough. So we have a spike here and some more stimuli that did not elicit a spike. And now if we were to increase the rate very much, you can of course have much more spikes, or we can have it decrease until the neuron does not spike. But please adjust the slider yourself so you can have 2 or 3 spikes that we can now use as target for the later network. So a value of around 27 or 28 should work, but you can of course try yourself. We are not all running the network on the same hardware setup today. So it may be the case that for you, you need a bit higher weight or a bit lower weight, as there are some differences even on the calibrated hardware. Maybe let's just go through the code for this cell again quickly. We again set a seed here before we draw the random weights. So this is helpful in order that when you adjust the weight, your trace becomes reproducible. Otherwise, it would just behave totally random. And it could be that you just lowered your weight mean, but you had more spikes because randomly they were a bit higher. And we configure those weights and run the network. And then we read back the data from the experiment. Mainly, we want to extract the membrane trace here that is sampled by the fast analog ADC. That's why we have this good time resolution here on the trace. And we simply plot it. Okay, if you have a few spikes on this graph, we can run the next cell, and this extracts the dynamic range of the membrane. As for the super spike rule, we will want to know what is a reset potential and what is a threshold in order to know if a neuron is close to spiking or not. So you should have at least one spike in this graph in order to correctly estimate the threshold, because we will now use the minimum and maximum of this trace in order to calculate a baseline and set the dynamic range. Okay, I'll just run this, and maybe before we dive deeper into the super spike rule, let me ask again, are there any questions, anything unclear? And did this work for all of you? Do you all see a few spikes in this plot? It seems to be the case. At least I don't see anything that would indicate that this is not the case. So then let's continue. The notebook worked great. Okay, the super spike learning rule. As I said in the beginning, we try to minimize the Van Rossum distance between two spike trains. This is designed as the difference in convolutions of your given spike train Si, convoluted with a kernel alpha, which could be an exponential. And that is subtracted from another convolution with a target spike train. So you can imagine that if the spike trains are very similar, the convolutions are also very similar and the difference is low. If the spikes would be at different times and the contributions from both is great, since we square that term, the loss would be greater in that case. So we will now minimize this loss, and taking a derivative with respect to the weights is of course complex because spike trains, you cannot so simply derive them. They are mostly zero everywhere. And the super spike rule by Friedemann Zenke arrives at this integral form for possible weight updates. And there are a few interesting terms here that we can investigate. So first, eta is simply a learning rule, simply a scalar factor. The integral now happens across times. So from start of the experiment to some time where you want to update your weights. And we integrate across three main factors. This is EI. This is the error signal from above. So here this Van Rossum distance is defined as EI for the lower term. And it is not yet squared, so we can have positive or negative error traces. And the rule will know whether we had too many spikes or too little spikes, basically, whether the weight update should be positive or negative. The other factor is a synaptic eligibility trace, and this is what we can refer to as this term in the square brackets here. And here, Sj is the input to neuron I. So we were considering the spike train Si of neuron I, and Sj would be the input spike train of synapse row J. So this convoluted with some kernel is a measure of the synaptic current that is arriving from synapse J at this neuron I. And this is now multiplied with the membrane potential Vi on the neuron, or a gradient of this. And I think we can say that this is this is a measure of coincidence. So basically, if your membrane potential is high and you have a synaptic current, this synapse is eligible to maybe trigger a spike in this neuron, or it is at least one of the more favorable ones to update weights if both those conditions are met. If the membrane potential would be very low, another input would not yet elicit a spike. And if there are no synaptic currents, of course, it would also not help to increase this specific rate. Now we have the membrane potential here, Vi, and we take a surrogate gradient sigma prime of this, which we will now investigate. There are multiple possible functions according to the paper of Friedemann Zenke for this gradient, but we will use this one here. And what these functions should do is they should peak at a high membrane potential. So we normalize the membrane potential here. One would be the spike threshold, 0 would be the lowest membrane potential or the reset potential. And those gradients should get steeper the closer you are to the threshold, so that, yeah, as I said previously, in this product of synaptic current and this superspike gradient, we can see that higher numbers mean that the neuron is much more likely to spike now, which is of course the case if we are closer to the threshold. The steepness of this function can be controlled by a parameter which we call beta here, and we can later investigate the effect of this parameter beta on the actual learning. Yeah, this cell here only plots the function for different beta. And we will now implement the superspike rule. There are two time constants that we need for that. This membrane and synaptic time constants. We will need them in order to have the convolutions. Alpha is a convolution with a synaptic, with a membrane kernel, epsilon with a synaptic kernel. And we will define those numbers as we have them from the calibration. And we will also define kernel functions for that. These are exponential kernels where we use e to the power of a time. The time is an increasing array in this case, divided by the tau that we just set here. So with our time bins, this kernel just matches the synaptic traces, the synaptic currents. And yeah, we have now an implementation of the superspike rule here in the last cells. And here we will train 100 epochs of superspikes. So initially we set the weights randomly so that we do not just reproduce what we had above. And then for epochs, we run the network in Pine. We retrieve the data, especially we retrieve the membrane trace and the spike times. And the membrane trace is first resampled to match the time bins that we are working with in the calculations later. So we have an interpolation here that resamples it to the time array that we had. And we compute an error trace. This error trace is the first term of the superspike rule. And it is only calculated using the difference between the target spikes and the actual spikes. So this is the measure of the van Rossum distance. It does not take into account the target membrane potential, only the target spikes. And the rate updates are now calculated for all the source neurons or all the synapses that we have in this column individually by first computing an eligibility trace for all the synapses individually and then computing this integral and taking the sum of it. So it's very close to that formulas that you have seen above. And yeah, let's just execute this cell and watch it train. So what you can see here initially is on the top a membrane potential that is compared to the target spikes. Lines here are the target spike times that we have defined in the cell above. And you can see that we do not have learned that here should be another spike. So this means that our error signal plotted here below is very high in this case, that we don't have another spike. And in case we do have a spike where we are supposed to have a spike, the error signal becomes very low, as we have a positive contribution here and immediately afterwards a negative contribution to the error signal that cancel out each other pretty quickly. And with each epoch, we are now updating the weights on hardware, waiting for another run, and updating the weights again. So hardware in the loop training, as you may know it. Okay, let's just run this, and maybe are there any questions so far? If not, I'll just wait a bit until our 100 epochs have completed. It takes 1 or 2 minutes. Not because the hardware would be that slow, but because all the overhead of running a single experiment is still pretty large currently. But it seems that we have completed, and we learned pretty closely to follow the target spike train. We can maybe quickly compare this spike train with the original spike train that we had. Try to remember a bit. It will not look very similar unless, so the spikes are at the right time, but the membrane trace in between will not be that similar because we are not learning on that. So we will have found another distribution. There's a question, what does Pine reset do? Will it reset the hardware? I think it will not reset the hardware, but only the simulator state, in the sense that the outputs that are returned from Pine are cleared and all that, but actually Christian may know that much better than I do.
Yes, I mean in Pine, in the software sense, so our implementation of Pine Run is a little bit off of the usual intention. So in Pine, if you want to run your experiment, one run is not the complete experiment in its whole, but a step of it. And when you call reset, you say, okay, now everything I did before is one part, then I reset it and can run experiments again. So for us, reset is more technical, that we executed to reset some states intrinsic in the software, but it doesn't correlate to a reset on the hardware in that sense.
It doesn't even do anything on the hardware, I guess, because
no,
only run will
it only
send programs
resets
to the hardware.
Yep. It only resets internal state of Pine, and basically says Pine, okay, save this now as one experiment chunk and start with a new one. But if you don't present it, it doesn't, in our current implementation, it doesn't really do that much. But in the future, this will probably change when we have a better support of really specifying specific points in time, so that you can, for example, after 200 milliseconds, also change the membrane, the leakage voltage or something like this.
By doing
yes, also, basically also the weights are resetted to the default values or 0 in that sense. So the only thing after a reset, the only thing that is kept is the topology, but internal states are resetted.
So in the cell here, the weight update happens via this set weights function that refers to the originally defined projections in Pine and sets those weights. We call run immediately afterwards. And the array weights here is local, so we keep this one even when Pine is reset, I guess.
But at the top of my head, I think this statement is not necessary at this point, technically. So you could just omit it and stuff would change internally, but in principle, it would do the same.
I think we need it because it also resets the time, the runtime.
Okay.
So that's why we need it. So we always start at 0 and then run, I don't know, like 200 milliseconds or so, microseconds. So that's why it's here.
Okay, if there are no more questions, we could quickly take a look at the parameter beta again. We had set it to 5 right now, which is not that high. And notice that when we started learning, did not have any spikes in the spike train. So we learned to increase the rates that far that we do have spikes. And we can try to increase beta drastically. So maybe try 50 and execute that cell again. And we will still have a similar membrane potential initially without spikes. But it will now have a much harder time learning that the rates need to be increased in order to elicit some spikes here. This is the case because this super spike gradient is now even steeper than the red curve. And basically, if the membrane potential is not very close to the threshold already, the rate updates become very small. So eventually, this will also converge, but not within the same time that it did previously. So this just as a quick remark on how the parameter beta affects our training. Okay, then I think we are done with this notebook also. And Jakob will now continue with plasticity demonstrations. Thank you.